the last topic for today. And today it almost felt as if we were doing 3 different lectures, as if we came Monday, Wednesday, Friday. So we are now on Friday, we are about to get to the end of the week. So local search. And I want to make sure that you realize that the local search that is in this particular cartoon is not the local search we are talking about. So we are not talking about give me all the hair salons closer to my house kind of local search. This is a general AI technique. It existed before the web local search came along. This is the outline. We are going to do several algorithms which get comprised, which are called local search, including hill climbing, gradient descent, simulated annealing, genetic algorithms. You may have known some of the words. You actually know about these algorithms already. This is a really simpler lecture. It's not as hard. Now, up until now, what we have been saying is that what we need is a path to the goal. We are starting from the start state. We want to get to the path. What is important is the path. I have to somehow get to the goal. Once I get to the goal, the output is how I got to the goal. And therefore, we have been relatively systematically exploring the search space, going one child at a time and slowly building up. We are going to make a slight twist. Now these are interconvertible, but for understanding we are going to make a slight twist. And the twist is that path is useless. What we want is a state that satisfies the goal test. And just the state itself is the part that we are looking for. Or we want a state which optimizes something. Slight difference. Up until now we were trying to reach the goal. Just reaching the goal was hard. We didn't know how we are going to reach the goal, which state will take us to the goal. Just reaching was the hard problem. Now I am saying is that we are now in the optimization world. We want to optimize something. Everything is a goal. I want to optimize it. So, here's an example. So I give you 2 ideas, right? One, where just getting to a configuration, a goal configuration is the important part. 2, where everything is a goal, it is the optimization that I'm talking about. And I'm going to merge these 2 also very soon, but let's take this example. 8 queens. When we are running example, we are trying to have a placement of queens such that no 2 queens are attacking each other, and it really doesn't matter how do I get to this goal configuration. What I need is a certain placement of queens which are non-attack. So do you see how it fits the first point that I was trying to make? The state itself is the solution, not the path. This is an important intuition. Is this a goal, by the way?
Nope.
Who is attacking whom?
The 2 tags.
Upper left and lower right.
Upper left and lower right.
Lower left,
No, upper left and
upper
lower
left, and oh yeah. So this is not a goal. So this is the sort of 2 sides of the coin. Goal satisfaction, just reaching the goal, and optimization. Everything is a goal. I want to optimize something. In fact, you can go back and forth between the 2 if you wanted. How? It's easy to go from. So if I could solve the satisfaction problem, no, if I could solve the optimization problem, then I will just create an objective function which tells me if I am in the goal or not. And optimizing that objective function will be equivalent to satisfying the goal. The other side is slightly tricky. If this is the only problem we could solve, then I can create different optimization bounds and try to do goal satisfaction. If I can satisfy the goal, then I increase my optimization bound and then satisfy the goal. And at some point, if I can't satisfy the goal, I have found my optimum. So really, these are 2 sides of the same coin. And we'll discuss this again next class, so don't worry about it if you didn't. Yeah.
What are you trying to optimize there?
Anything, some of them.
So do we have a start state concept here, or is it like we are trying to build the goal state, something like
We are trying to build the goal state.
place the queen based on certain rules,
Yes,
and then
yes.
we filter out.
Yes, yes. So we are in the second category. But in general, these are two sides of the same. In terms of complexity classes also, they are usually in the same complexity class. So this is what we're going to do today, right now. Local search keeps track of the single state. That's why it's called local. It has no understanding of how it came from, what search tree got explored, nothing. The only thing it knows is where I am today, right now, at this present moment of time. It lives in the present. Isn't it nice? It moves only to its neighbors, and that is why it's called local. Right? A star was moving along the frontiers. There was no way it was local. This is local. It's only moving to its neighbors. It doesn't care for the paths. It has a very obvious advantage. What is the obvious advantage? It's not using any memory. Forget exhausting the machine. It is not using any memory, or basically no memory. Current state and its neighbors. That's it. The biggest advantage, and that is why I gave it to you as an assignment, is that if you really have a large problem to solve in the real world, local search will solve it. But there is no magic, so it will not give you an optimal solution, it is not complete, there may be an answer, you may not find it, all of those things will happen, but it will scale much faster. It will give you something reasonable pretty quickly. And that is the reason why I thought you should learn to get practice with local search, because you are working with real problems. So, local search models everything is a pure optimization problem. So these will be the characteristics. All states will have an objective function. So we'll be evaluating the state for some property, and our objective, our goal will be to maximize or minimize that objective function, to optimize that objective function. Excuse me. And therefore it does not fit really into the path cost goal state formulation, although if you think a little bit more thoughtfully, you might be able to convert it, but we will not get there. So, now n queens. Is it a satisfaction problem or an optimization problem? Any ideas of how to convert it into an optimization problem?
How many queens are attacking?
Yeah, how many queens are attacking each other? How many queens means how many pairs of queens?
Yeah. Oh, okay, yeah.
How many pairs of queens are attacking? Very easy, right? That's what I was saying, that you can easily move back and forth. So here we just saw how to convert a satisfaction problem into an optimization problem. Very simple. So, number of pairs of queens that are attacking each other. In this particular case, the answer is 17. So you can actually try this pair is attacking, this pair is attacking, this pair is attacking, this pair is attacking. And what will be the optimal solution? 0. So you want to optimize this h value. So by using this idea of a heuristic again in a very different context, I can convert a satisfaction problem into an optimization problem. As with any search, we have a search space. So in this case, the search space is the state itself. So even in the previous one, it was the state. So the word state. But here it is the complete configuration. So the solution, so here's the insight that you need to remember. In local search, always the solution is the state. I start with a complete solution to the problem in local search. That complete solution may be really bad, may be infeasible, maybe may have bad heuristic value, whatever it is. But I start with a complete solution. So in the case of n queens, I will start with a complete placement of the 8 queens. That's what I'm going to start with. They may all be attacking everybody. They may be in the straight line for all I care. But it should be a complete solution. Because we are looking for that state which has the optimal value. If we find that state, we should be able to output the solution. The only thing we remember is my current state, So my current state should have all the information required to generate the solution, and therefore the state is the solution. Now, the second thing I need to define is a successor function. A successor function would be some modification to my current state that takes me to some part of the neighboring state. Any ideas of what might be a good solution for n queens, a successor function?
Move the queen vertically.
Move a queen vertically. This will never work if my initial assignment did not make sure that there was a queen in every column. I don't think most people got that. But if my initial solution made sure that there was a queen in every column, then move the queen vertically is enough in the long run to generate the whole state space or explore the whole state space.
Would it be a better function to move one of the queens that's under attack rather than just any queen?
Depends. But it's a fair successor. You may hit a local optimum, but we'll talk about it using words that I have not introduced so far. Okay. So, before I get into local search, let's think about a couple of other things. For n queens, can I define a really trivial algorithm which is generate a random solution? How can I generate a random solution? Pick a queen, place it randomly in the first column. Pick another queen, place it randomly in the second column, and do this random assignment. Right?
It's a
Is
random
it-
candidate solution.
Sorry?
It's a random candidate solution.
It's a random candidate solution. If I just did this, and then redid this, and redid this, and redid this, is it a complete algorithm?
No,
Why not?
because you might end up with the same stuff you've already done. It's random, so there's no guarantee that you won't repeat previous states.
But if there is a solution, will I get to that solution eventually?
Yes.
Infinite time.
So
Yes.
uniform
Yes.
distribution, what's the distribution? You tell me the distribution of your random variable.
The distribution, I just told you the distribution for n queens, for example.
Uniform distribution, then
Yeah.
then I think you. with
So as long as you are not
some-
starving any state in your random assignment, so it's very interesting. Just this random generation is asymptotically complete.
Question you have to ask yourself is, do you feel lucky?
Are there any Googleites here? Google doesn't feel lucky anymore, right? Stop feeling lucky.
Just not.
So, that's actually very interesting observation, right? The second observation is that we can do random walk. So what I just described to you is random sampling. A second trivial algorithm is random walk. I have a neighborhood function, I randomly pick one. I have a neighborhood function, I randomly pick one, do this, keep doing this. And as long as my neighborhood function is such that every state remains reachable, this is also a computed solution. Again, asymptotic.
What do you mean by neighborhood?
I just described a neighborhood, or he just described a neighborhood, which was move any random coin to any random point in its column. So I have to define some neighborhood function that goes from one candidate solution to another candidate solution. Okay, so now we are done with the trivial algorithms. It's pretty cool. The really trivial algorithms are asymptotically complete. They get to the optimal solution in the limit. Yeah, of course. They're trivial algorithms. If intelligence was trivial, you know. So now I'm going to describe the only main algorithm in this lecture. It's called hill climbing. And I'm guessing half of you know this. How many of you know hill climbing? Wow, fewer than I expected. Okay, so let's make sure that we understand this. So I'm going to start with an initial state, and again, state here is a candidate solution. I'm going to start with an initial candidate solution. Let's call it current. I look at all its neighbors, and suppose I want to maximize. I'm going to pick the highest valued successor. highest valued neighbor. If that neighbor is better than my current solution, then I'm going to repeat. If all neighbors are worse than my current solution, I'm going to stop and return the current solution. That's it. Make sure that you stare at this algorithm for some time and make sure you understand this. Look at my neighbors, go to the best neighbor. Look at my neighbors, go to the best neighbor. Keep improving the objective function. If all the neighbors are worse than me, then I am the king, we stop.
How do you distinguish between equal? So like two neighbors are equal B value.
Yeah, so I think this is correct.
So you choose any one of them? That's what
Yeah, you randomly pick, random tie breaking, exactly. And if it's a min, then just reverse this inequality, that's about no other change. This is called greedy local search or hill climbing. Okay? And this is the main algorithm that we are going to start from today. I mean in this part of the lecture. Here's various ways you can think about this. It's a loop that continuously moves towards the increasing value and terminates when the peak is reached. This value can be some objective function that is given to us, or a heuristic function that we created for solving satisfaction problems. It is myopic. It is myopic to the core. It does not look beyond its immediate neighbors. Just does not. And if you have multiple successors with the same best value, it just randomly picks. Yeah? So the best way to describe this is what we should never do in real life, but that's what the algorithm does. It tries to climb the Mount Everest in a thick fog. Why is there thick fog? With amnesia. Why is there amnesia? Exactly. One would think, why is such a dumb algorithm? The good algorithms to study. Anyway, it has really, really nice properties. I mean, in practice. Okay, now, a way to understand greedy local search is to think about the space, the landscape of solutions. So this is my landscape of solutions. This is the global maximum that I probably want to reach. Do you think that greedy local search is always guaranteed to reach this point?
No.
Give me one example where it might not be able to. Exactly.
Actually, I can say with some authority, it will reach it probably, what, a third of the time? Less than a third of the time?
What's the wing random stars?
Please don't run ahead of me. So, if we started here, we probably reached this point, and it's called a local maximum. It's a maximum because in an immediate neighborhood, it still looks like an optimal or a greedy a peak, but it is not the global peak. It's a local peak. There are some other interesting artifacts in this landscape. One of the other important artifacts is something called a shoulder, where all the values of the successors is the same. Or you're not increasing the values. The question is, what do we do in a shoulder? So here's an example. 8 coins. Randomly generated 8 coin starting states. Okay, so starting state is important. If I randomly generate a starting state, then it solves the problem 14% of the time. One would think, bad, if it only solves the problem 14% of the time, why
So
bother?
run it 5 times.
Wait, again, you're running ahead of everybody. Maybe everybody is with you and I'm only the slower one. So, the interesting thing, I think this is important to note, this is very important to note, that when it succeeds, it takes 4 steps to get there on average. So, starts with a start state, makes a move, makes a move, makes a move, makes a move, gets to a solution, 14% of the time. And when it fails, it fails in about 3 moves. It gets to a local optimum, cannot satisfy the n queens configuration, it fails.
This was statistically computed or
Yeah, yeah.
theoretically proved?
Statistically computed most likely.
That's really fast.
So now we are talking about a state space of size 8 to the 8. 17 million states. And 14% of the time we can solve it in 4 moves without using any memory. Alright, let's keep moving. We'll come back to this point. So I'm sure within your mind you are thinking about ways and means to fix this algorithm already. So I mean, that's, yes, Harun.
The previous slide you mentioned that one step means moving all 8 queens one time.
Moving any one queen one time.
So getting stuck in this case is like you end up in a state where you can't reduce the
You
number
can't just move one queen
and
and get to
lower.
a configuration which has lower number of attacking pairs. There are various problems in local search. One that you have already seen is called local minimum. Because if your state space is very rugged, then what is going to happen is that you will be stuck in many of these points, and until you start in this particular point, you are not going to get to the global optimum. And again, most of these are not two-dimensional problems, so they are multi-dimensional problems, so it's even harder. The other problem is plateau. What do we do when we have the objective function is not changing? There are other subtle problems that happen. So here is a subtle problem called diagonal ridge. It says, think of it as two-dimensional problems. Suppose there is x, y, axes and so on. So in order to get from here to this point, suppose I have to change both x and y. Okay. But my neighborhood function is defined so that I either change x or either change y. So now, in order to get from this to this point, what will I have to do? I will have to first change x. To change x, I may actually have to come down, then change y, and go up. And if there are many of these ridges, I have to go down, go up, go down, go up, go down, go up, and eventually get to the point. These are called diagonal ridges. Very hard, makes local search really miserable because it keeps getting stuck in these local optimal points.
So it treats them as local optimums,
Yeah.
although
Yeah.
they actually are not local optimums.
They are local optimums
views
because all the
perspective.
successes are lower value
Yes.
based on your definition of the success. Okay, so let's try and fix some of the problems. So let's start with the first easier problem, plateau. Okay, give me a solution to fix the problem of plateaus in local local search. Yes, right.
Explore horizontally for a limited
Yes.
distance.
Let's just allow moves which are same. It's called a sideways move. So, now, what if it's a really long plateau? Then I will keep going, right? So let's make our life reasonable and say I'm going to only allow 100 sideways, something like that. So keep a count. So, if there is no downhill move, if there is no greedy move possible, allow sideways moves, hope that algorithm will be able to escape. For 8 queens, if we place a limit of 100 sideways moves, this is what happens. You can now solve a problem 94% of the time. However, a successful solution takes now 21 steps and an unsuccessful solution takes 64 steps because we are allowing these sideways moves. You had a question?
You may be doing one backtracking because you have amnesia, right? So
Yes.
your predecessor may be your next successor.
Yes. Do you see this problem? You might just be repeating yourself. You went here, sideways, 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 and then you came here, you came here.
Unlikely in this case. There's a lot of state, and the chance of you moving one back the same way as 1 out of 8 possible moves?
Yeah, but you may come back again after
Yeah, you might.
3 months.
12% of the time that will happen.
Yeah, but we're not just trying to solve 8 queens, we're trying to develop general awareness. What might you do in order to fix this problem, by the way?
Either plateau.
Yeah. You say, I am doing sideways moves. It is quite common for me to come back to the same move, same point, because my objective function is not changing in these moves. Let me use a little bit of memory and disallow all the states that I have just visited. Let me taboo some of those states that I have just visited. It's called taboo search. And this is not a typo. So we keep a fixed length queue called the taboo list. Add the most recent state to the queue, drop the older state, never make the step that is currently taboo. Now, let's think about this a little bit. If my taboo list is 0, we are greedy local search. It is sideways. If my taboo list is huge, let's say the whole of the state space size. Now I'm more or less systematically exploring the state space, right? Because I'm never revisiting a state space, the amnesia is gone, I have infinite memory, I am making sure that I never revisit a state. So you can think of taboo list or taboo search as one sort of a point in the middle of greedy local search and systematic search. Does that make sense? Because I'm using some memory, it's somewhere in the middle. I'm not systematically exploring the whole state space, but I'm still making sure that I am not revisiting the states that I just visited. An intermediate point. Yes?
I'm Nat.
You are
so-
that?
Nat.
That.
So when you get out of the plateau, do you then flush the list?
You don't have to, it will naturally get flushed, but you can. You don't, in implementations, people don't just keep adding and deleting. Yes.
So why would you ever have the taboo list more than the sideways limit? So sideways limit is
Yeah.
100,
In this particular example, there is no sideways limit.
but in general, like if you have a sideways limit,
Then
so
you don't need
either
it.
you be equal or go down. So you can't never come back if you are not going to.
Even in sideways list, your taboo, yeah, okay. So if you have a sideways limit, then your taboo search should not be greater than that. You can have taboo search without sideways limit also. You just keep going.
Why? If you always go down, how can you come back to the same point again?
You're not going down, you're either the same or going up.
Yeah, that's what I said. You never go down.
Yeah, exactly.
So how can you come back to the same state?
If you're just making sideways moves.
So sideways moves is essential to come back to the same state. And if you are making sideways move, there is this length of the taboo list has to be equal to
The sideways
side.
move. Now,
So point I was trying to make is if you don't have sideways move, this doesn't make sense.
You don't know if
Well,
you're gonna have
stop
it or
and
not.
think about what sideways moves in a 14-dimensional geometry, and it may not be so simple.
You don't know whether or not you're gonna have sideways.
no, okay, so
No.
I think we're missing the point. I agree with you, all your points. So if you have a sideways limit and you are never going down, then your taboo list size need not be greater than the sideways limit. I agree with that point. The assumptions are wrong. So what will happen very soon is that we will allow moves that allow us to move down. We're building up slowly, one at a time. So right now local search was just going up. Sideways move says I'm allowing not going down but staying the same. Very soon we will actually also go down. So we'll get there. One step at a time. Usually people do taboo list of size 100 and so on. Again we are talking discrete problems, 14-dimensional continuous spaces are harder for this. Yes, Anbara.
So do I move and do like left or right? Because if I'm like writing a algorithm as a pattern, I'm always gonna move right each time we get start from a certain state. But if the solution might be right to the left. If I wanna go up, I should have moved to the left. So my question is, if I have equally weighted states, either in the side and I'm allowing sideways, which one do I get?
randomly. Okay. And if you have taboo search, then I make sure that I don't repeat it, but I pick randomly. Okay. What else might you do if really escaping the shoulder was absolutely of utmost importance?
A big jump.
How do you make a picture?
Random generator.
Yeah, but I'm thinking more about, I am at a shoulder, I want to improve my objective function and escape the shoulder, what should I do?
Take
Increasing
a less
the-
optimal step
Like
and then
Newton's
start off
where
with
you-
again.
The jump size you make is proportional to some sense of the tangent.
So jump size, so you're saying that I look farther in the future, right? Not just look one step, but look for,
Take a
bigger
look at
steps.
the
Again, don't think
gradients.
continuous necessarily, think in the search framework, more
Yeah.
history. So as I was saying, taboo search is a point between local search and systematic search. There's another point between local search and systematic search. It's called enforced hill climbing. The reason it's called enforced hill climbing is because we are enforcing the fact that we have to climb the hill. So if I am in a shoulder, then I do systematic search. I actually start doing breadth first search and hope that at some point I'm going to find a point which is better in my value, optimization value, and then I'm going to forget all of the breadth first search, move to this point which is better, and start doing hill climbing. And that's called enforced hill climbing. Again, it's a middle point between local and systematic search, but it's a different middle point than taboo search. And typically in practice, because exhaustive search is very expensive, what happens is that there are prolonged periods of exhaustive search and it's bridged by relatively quick periods of hill climbing. This particular algorithm was developed in the context of planning, which we will discuss 3 weeks down the line, and that was because that search space had too many shoulders. And so you had to develop some algorithm that can escape those shoulders, and they developed enforced hill climbing.
Getting to the first one might get to the local optimum.
You should, yeah. But then we will do systematic search from there. Now, up until now we have only been doing deterministic algorithms, but we can also do stochastic algorithms. So stochastic version would be, okay, the greedy local move said that I'm going to pick the best successor. But a stochastic greedy move would be pick one of the many better successors with different probabilities. And the probability can be weighted by how good they are as a start. It's called stochastic local search, stochastic hill climb. Now, this randomization can also be used to make these algorithms complete. So local search is not a complete algorithm. Greedy local search is not a complete algorithm. Enforced hill climbing, maybe if we allow infinite exhaustive search, but that's too bad. Now, in the very beginning, we did some trivial algorithms which were complete. Of course, they were bad. They were trivial. So the question is, can we do a combination of the two that probably has slightly better properties and is also faster? So what we are going to do next is random walk hill climbing and random restart hill climbing. So let's do the random walk hill climbing. So it says I'm going to make a greedy move with some probability, and with 1 minus that probability I'm going to make a random move. That's the only thing it says. Very simple. So with probability P, high probability P makes a greedy move. The probability with minus p, small probability with minus p makes a random move. The combination of the two is guaranteed to be asymptotically complete. Can you think of what would be random restart hill climbing?
Randomly go somewhere else. Like normally you're doing the hill climbing, but at some random point in time you'll just jump to some other point.
Exactly. So another way of thinking about this is, there are two variations, but let's do the nicer one first. It says, If you don't succeed, try again. So I'm doing greedy local search, I get to this local point, okay? Then I randomly find a new starting point, keep going up, get to this local point. Then I again pick a random starting point, keep going up, get to the local
You find it to a local minimum, local
maximum, and then I
once
move.
you've gotten to the local maximum.
Maximum, then I move. But then there is the version that Zan was suggesting. Don't even wait for getting to the local move. With probability P, make a local jump, and with probability 1 minus P, make a random jump.
Do you remember your previous local maximum?
You always memorize the best solution found so far.
But we don't know whether or not.
Yeah, you don't miss. If you have seen a better solution, you always remember it. Obviously.
Can you say what you just said?
With
The jump?
with probability P, make the next better step, greedy step. With probability 1 minus P, get to some random point out of
Random
nowhere.
initial state, I think.
Random initial state. So again, this is asymptotically complete. But let's do the analysis of the version in which we run until we get to the local maximum and then we move to the next starting state. So remember that with 14% probability, 8 coins was going to give me the correct answer with 4 moves, and with 86% probability it was giving me incorrect answer, local maximum, in 3 moves. So if I just did random restart until completion, then in about 7 retries, in expected sense, I'm going to get to a solution in about 21 steps or some numbers. Trisha.
So when you're randomly restarting, how do you know that that restarting point is the one that you tried in the past?
No, you don't know.
So you just randomly,
You just
even
randomly
though
go.
it's there.
But it's random, so the probability of that is not.
How do you compare these random algorithms? I mean,
I-
apart from that,
At this point, I don't really care for theory. I'm telling you things that work.
no, like which one to choose?
Yeah, so that I don't know the answer to that. So you have to try. It's an empirical question, and different algorithms will work differently
On
But-
the specific problem.
on different problems. But if I have to give you one algorithm that you need to memorize from this part of the lecture, one algorithm, and you say that too many of these, I can do this with this probability, I can do that with that probability, I can do stochastic, I can do sideways, too much, then memorize this one. Go up, go up, go up, go up, hit a local maximum, randomly restart, go up, go up, go up, go up, hit a local maximum, randomly restart. See? So do deterministic, greedy local search up to the peak and then randomly restart. This particular algorithm, in practice, by and large, gives you better results
For many problems.
for many, by and large. Okay? We'll keep moving. We'll do other algorithms. This is the one to remember. And the first algorithm that you will have to implement in your project would be this one. So I don't think we'll get to talk about the project today. So what I'm going to tell you is the following. I've given you one problem. It's a problem that you have never seen. It's a new problem. It will be very clear from the assignment description. You have to think about a local search solution for it and first implement this. This will be your baseline. And my guess is that for half of you, this will be the best solution that you will come up with. And then there is the creative part. Then you think about the problem, actually deeply, and you come up with your algorithm. Your algorithm can be based on local search, can use any knowledge about the particular domain of interest, can use heuristic search, A star, whatever you want to use. Okay? And submit your best algorithm. And then in the end, when we have all the algorithms, we will test it on different problems, and you will all come up with your values, your best values for those problems. And the winner would be the one who has the best average.
Which means the winner is totally random.
Sorry?
The winner is totally random.
Yeah, but
These
there is
random
some.
algorithms.
These are all randomized algorithms. You may have bad luck, but usually in practice that doesn't happen.
Is there any restriction on algorithms or?
No. There is restriction that you cannot use linear programming or integer linear programming. But it will be clear, but if you have questions, please ask. And then you can do hill climbing with both. So both here will mean with some probability move to the greediest neighbor, with some probability to get to a random neighbor, with some probability to do a random restart. So bottom line is that once you understand this set of algorithms, you can just do whatever you want. That's it. That's all it is. Okay. Here is another algorithm that we should discuss for completeness. So the bigger problem with local search is that it gets stuck in local optimum, right? So it's like this: you drop a ball from the top of the hill, and suppose you want to have it reach the river at the very bottom. Keeps going, keeps going, keeps going, keeps going, and at some point it gets stuck in a small valley somewhere, in a small ditch somewhere. Now, if you really wanted the ball to go back to the river, what would you have to do? You have to shake it. To shake the earth. And then suddenly it will just pop out of this ditch and starts going down. And then again you have to shake it. That's simulated annealing. So the idea is, this algorithm says you figure out the best move if it is going down or if it is going up, as in if it is hill climbing, move to this state. If it is not hill climbing, if the objective value is worse, then you still move to this state with some probability. Delta. But this probability changes with respect to how much you are shaking. So again, I'm at a state, I pick a neighbor randomly. If it is improving my objective function, I get there. If it is not improving my objective function, I may still get there with some probability. But that probability is now because I'm making a negative move. I'm making a move in the reverse direction. Excuse me. I make that move with the probability that is proportional to the amount of shake. It's also called temperature. So that shake is vigorous initially, and that shake slows down later. If I slowly reduce my shaking from vigorous to not much and to 0, then it is actually guaranteed to find a global optimum. But that shake is very slow. Now I'll give you the physics analogy. The physics analogy is that there is a process of cooling of a liquid. So there are all these spins in this glass which are randomly behaving, and the configuration is the least energy configuration. And the actual spin depends on the spins of all the neighboring glasses, particles. If the temperature is high, then they can still be, it's equivalent to more shake. They may be in high energy configurations. But as the temperature reduces, they cool down slowly, they cool down to the lowest energy configuration. So that's another analogy of simulated annealing. So the temperature tells you the probability that it is, I'm going to take a negative move. Okay. Same intuition. So you can read the details. This algorithm has been very popular in the VLSI community actually. So it was originally invented in 1983 by IBM researchers who were trying to solve these VLSI layout problems, and simulated annealing is still used in those situations. And it has been extensively used in the past in traveling salesman, graph partitioning, lots of problems. It is useful, but in my personal opinion, it can be extremely slow, because in order to get to this global optimality, I have to reduce my temperature or my shake really slowly, and so it doesn't work out. So in practice, if you're more empirical minded, you want to make things work in practice, just do hill climbing with random restarts and you will be fine. You don't have to really do too much of simulated annealing, but it's a good algorithm to know because it's guaranteed to achieve global optimum in practice.
How can it be guaranteed? Like it's continuous, the rate that's just low would be.
So because you're shaking, it just keeps coming out of local optimum over and over and over.
It's
guaranteed for every graduation of T, or there is a?
No, very slow schedule. You have to have a schedule of temperature that slowly reduces.
But that slope could be like,
Yeah, exactly. So that's why I'm saying it's not useful in practice. That's my point. But you can prove that there are schedules which really slowly reduce that in asymptotically they are guaranteed to. I mean, random sampling is guaranteed to get to optimal. So what's the big deal about being complete? But I want to get to a couple of other interesting algorithms. So there is another algorithm called local beam search, and the idea there is. This amnesia business is ridiculous because I'm only storing one state at a time. I really have 2 gigabytes of memory. Why am I only storing one state at a time? At least I can store 1 gigabyte of space, right? Something like that. So it says instead of just start having one state, do keep track of k states. And then you have a beam of k, and then you look at the successors, and then you keep the best k. Now, is it same as doing k different problems in parallel? No, because 2 states can be from the same hill. In fact, many states can be from the same hill. Because I am actually getting all the successors and keeping the best k. So it is not equivalent to doing k trials in parallel. In fact, that is its problem. Because even if you start from diverse starting points, what happens? Very soon all of them get to this particular hill. So what can you do about it? Randomize the successor picking. It's like you guys are researching algorithms right in this class. So it's called stochastic local beam search. The idea being instead of choosing k best successors, choose k successors randomly, bias towards good ones. Now, here comes the interesting part. And most likely we won't cover it today, but that's fine. All of this business, this stochastic local search business, let me remind you what the idea is. I start from k points, I look at all the neighbors of these k, and I stochastically pick the better ones. And that is my next k, and I repeat this process. This sounds very close to natural selection. Right? You have a population of k, and you could have children, and then you pick the best k children, or stochastically the best k children, and now you have a population. Of course, that's not real natural selection because mankind is going like this, the population of mankind, but suppose.
Eugenics.
But this is not our natural selection. This is amoeba's natural selection, or microorganisms natural, because this is asexual reproduction. I can generate many children by myself, right? So this is asexual reproduction. So now we believe that our mankind has all the nature goes by sexual reproduction. So why should we do asexual? So maybe we can use our genetics to improve local search. So of course Darwin comes along and says, yeah, check my book. So let's evolve n coins. Let's finish the thing that we had started last time, which is genetic algorithms. And after that, let's talk about the assignment, any difficulties that you may be having before moving on to the topic of the day. So I apologize that I rushed through genetic algorithms a little bit last time, so let's just go a bit slower, make sure that we are on the same page, and then move on. So we started from doing local beam search, and the idea there was that instead of keeping just one node in the memory, and I'm assuming that most of you remember local search because you are working on it on your assignment. So instead of just keeping one node in the memory, which is my current state, and moving around, that's just wasteful. We are wasting all the remaining 1.999 gigabyte of memory that typical machines may have. So what do? Instead of keeping just one state, let's keep track of k states. Let's randomly start with a suite of states as my initial states, and then let me move forward and do neighborhood search, local search on the k starting points. The only difference is that I'm not doing k searches in parallel. What I'm doing is at every step I'm generating lots of successes for all these k initial starting points, and then choosing the top k successes. By choosing the top k successes, the successes that don't look too good are sort of lost. So some of the starting points are lost, and some of the starting points come in more prominently in my set of k. That has the problem that if there are multiple hills, then slowly, all the points may congregate into a single hill, which may not be very good because you want some kind of diversity. And so instead of doing this completely deterministic, you can do a stochastic version of local search, local beam search, which is stochastic beam search. And instead of choosing k successors, which are the best k successors, choose the k successors randomly, but bias them towards the good ones. So this was the starting point. The point to make was that this has a huge close analogy with natural selection. You have lots of these organisms, the starting points, and they're all reproducing and they are getting some children or successors, and the best ones are maintained in my world, right? And I'm assuming in this scenario that the population of the world is not increasing. So it's very close to natural selection. What is missing here is a bisexual reproduction, or two organisms coming together to make a successor. Right now what we have is asexual reproduction, where you have one node and that is generating its successors using mitosis or what have you, meiosis. So far so good? Are you finding it hard to swap in local search? No. Okay. So that led us to asking the question: can we just take what we observe in the in world, on Earth, in nature, and reproduce it, pun not intended, in local search? So here is what genetic algorithms say. Genetic algorithms say that we have the same notion of local beam search. We have a population. We'll just use the words that are common to natural selection, but it's the same idea. So we will have k randomly generated starting points. That will be my population. And then I will have some notion of a fitness function, which I already had in the previous as well. That's how I was ordering my successors, right? So I have some notion of evaluation function. The only thing is that I'm not going to be minimizing this. It will be a maximizing function. It's some notion of fitness function, how fit I am. And then what I'm going to do is that I'm going to do random selection, right? So based on my fitness, I have some probability of living or dying. I'm going to do crossover, which is the closest analog to how genetics works. And then I'm also allowing random mutation. And then if I have these scenarios, what happens to my new population? So let's look at the example. So we will think about a string representation. That's very common in doing these. So often this is my board, and my string representation for the n queens problem can be that the queen in column 1 is at row x, queen at column 2 is at row x, queen at column 3 is at row. So that gives me a string representation. Everybody okay with the string representation? Seem to be more sleepy today than before. Looks like you guys are working hard on the assignment. Alright, so I have this string representation, and then I'm going to define some fitness function and forget the joke. So the fitness function is the following. I can test how many pairs of non-attacking queens does my configuration have. And that tells me how fit my representation is. So earlier we were minimizing the number of attacking pairs, but now let's say that I want to have fitness, the maximization analog of it. So I'm going to count the number of non-attacking pairs. And now I know that the minimum number of non-attacking pairs would probably be 0, and max in this particular example would be all pairs, so 28. Now, I can evaluate this count for each of these individually. So this string evaluates to 24, this string evaluates to 23, this for 220, this to 11. And what fitness function analog of natural selection, so basically what random sampling does, or natural selection does, it says what is my percentage of being fit. So for example, these are the total individual fitness count, so let me add them, that creates my denominator. And so this particular, so the denominator becomes 47, 67, 78. So my denominator is 78. So I'm going to say that this particular individual is fit, his fitness is 24 over 78. This particular individual's fitness is 23 over 78. This has 11 over 78. And so that tells me a percentage of how fit they are. Now I'm going to take my sample of K population and just randomly, with replacement, select the new sample by using these percentages. So with 31% probability I'm going to select this guy, with 29% probability I'm going to select this guy. So as you can see, this particular guy got repeated twice and this particular guy just died. Which is good because this guy was not very fit.
So, question.
Yes.
What's the significance of the mutation step here?
Coming to mutation. But right now, are we okay with the natural selection part? So now I have selected a new generation. This is my new generation, right? Now I'm going to do crossing over. Crossing over was the notion of getting two individuals and creating a successor or multiple successors. So in this case, we can define our crossing over as follows. We can say that we'll find a cutting point, and then we'll take left part of this guy and right part of this guy, and left part of the second guy and right part of the first guy, and create two different individuals.
Cutting point is random too.
Cutting point is random too, exactly. So now we got these guys. Now the mutation step says, I'm going to just come, that's what nature does, right? It just comes and suddenly changes some symbol somewhere in your genome sequence. Why do it? With what probability to do it? That's a difficult question to answer. But this is the closest analog to how nature is working. Two people come together, create a baby, the baby has a crossing over point, that's how the chromosomes work, and at some natural random mutations also happen once in a while. That's exactly what is happening.
But there should be like some intuition like in what it will help. So one problem is like as you keep getting closer to even a local maxima, stuff starts to converge. By that I mean that all those states will become more and more similar to each other, which is how it converges, right?
Right.
So is it to get out of that?
Precisely. Precisely. Precisely.
But you're just changing one bit.
No, you can change two bits. So it's again, it's a probabilistic notion. So you can change multiple bits with different probabilities. So again, we will talk exactly about this question.
So like, do you do random restarts here also?
No, we do not do random restarts.
So once
Typically in
you
genetic
are
algorithms.
pretty much stuck at a local maxima.
Yeah, so if you have converged your particular population and you're not happy with the results, nobody is stopping you from restarting the genetic algorithms from a different starting point. I don't know if genetic algorithms typically restarted over and over.
They won't get stuck because of the mutation.
Wouldn't they be?
They won't get stuck because of the mutation.
They won't get stuck because of the mutation is also a good point. That's exactly what you were. Okay. So I think the more interesting question, mutation is okay, but the more interesting question is what is crossing over doing first? Why is crossing over interesting? And crossing over is interesting because it is allowing you to take a relatively non-local jump. That's the key point. See, typically when we define an operator space, we defined it for n queens. What we said, okay, let's take one queen and just move that location of that. That's exactly what mutation is doing in this case, by the way. Not something out of the ordinary, really. But what crossing over is doing is that it is saying I'm taking one part of this guy and the other part of that guy and joining it. There is no way I would have started from this person and or this state and in one step or a couple of steps got to this point. The neighborhood function will typically not allow such large jumps.
And one more thing is like they are likely to be good solutions.
Say that again.
So you are making a jump to a potentially good candidate.
If these are good guys, then you are making a jump to a potentially good guy. That's exactly
if you
how.
select good guys, right? So
Precisely. That's exactly what genetics.
A jump to a good.
That's exactly how genetics works. But if you have two good individuals, they make a baby. It's a good chance that that baby is going to be much stronger than both of the babies. Yes.
But both solutions are good in their own respects. Half part depends on the other half. When they combine, then it's not necessarily
But
be a
if
good
they,
solution.
precisely, and if they are not good, then the next natural selection is going to get them off. But by luck, you might get to a good solution, and you'll just improve it.
So even after doing crossing over mutation, the sequence that we get, we are supposed to check the fitness of that and then pick or.
So no, that gives you a new population. But then you repeat and you do again a random selection move in the next iteration. So you have a new population of K, then you redo random selection, some of the non-fit ones. So you keep repeating this process for a long time.
Could we choose the 50%, like less 50% of the initial population, plus 50% of the next selection, and then?
You can do whatever you want, but that's true for local search in general.
I can preserve the whole history as well.
But usually, I haven't heard, but I'm not a genetic algorithm expert.
So if we do the crossover and turn out that this is a really bad combination, then next time when we do another iteration, is it gonna drop out because the
Quite likely.
iteration test won't pass?
Quite like,
Okay.
yes, exactly.
K is usually constant across generations.
K is usually constant across questions. Yes. At least on machine, we can make sure that the population of the world does not increase.
What about like trisexual reproduction?
Yeah, you can do whatever you want, as I said. Manage it, whatever. So, some comments on genetic algorithms. First of all, I think that's how I introduced it. It's a variant of stochastic beam search, right? It's a special kind of version, but it's a variant, right? The interesting part is that sometimes this random exploration, because of the crossing over, is able to find solutions that local search is unable to, typical local search, right? Because it's going one step at a time. And what is also interesting is that it is fun to teach it in the class. You get lots of questions because you start thinking about what you know about the world, and all those analogs start coming into the play. But at the end of the day, it is important to realize that all these notions, genetic algorithms or neural networks, all of these are metaphors. At the end of the day, it's a computational algorithm, and it's metaphorically conceived somehow or the other. Again, no pun intended, but so right now, a typical criticism of genetic algorithms is that there are just a ton of parameters. How many? What size of the population do I start with? With what probability do I do the mutation? How much mutation do I do? We are talking about how many individuals to create new individuals. If I do crossing over, do I create 2 individuals, or do I create 3 individuals, or I can basically if you started to actually implement this, you will find that there are lots of problems. And so what happens is that once in a while somebody comes along and says, I did this using genetic algorithms and this was so awesome, and it worked. But then somebody else tries to replicate it based on what this person came up with. Unless you have the exact implementation or the exact parameter values, somehow this you are not able to replicate the results, and that's somewhat less exciting. And in practice, what people by and large have seen, again, you will see that this is AI, so every algorithm will work great for some problem, right? But by and large, again, you have to make some generalizations because we are doing a course. The method that I would suggest you remember, if you have to remember one algorithm, is hill climbing with random instance. Exactly. Okay. So that is the thing that would be more or less fine for a lot of the problems, as we discussed last time.
What kind of problems is GA good on?
So I don't know the answer to that.
So I know that it's been applied to discovering bone structure from. So basically, if you have so there are these paleontologists who do studies on prehistoric bits of fossils, and they want to infer the exact shape of the bone and stuff from limited evidence. So what they do is they use some kind of genetic algorithm to basically optimize the flexibility of the hand given some parameters of the bones and stuff like this. And this is one example in biology. And I guess there are lots of examples. But usually, as far as I know, it's a last resort, when nothing else works.
So, but I want to definitely give you another example of genetic algorithm, just so that you know that crossing over can happen in many ways, mutation can happen in many ways. So are all of you familiar with traveling salesman? The goal is you start from one city and you have to go through all cities, and you have to reduce the total cost that you pay of going around. So what would be a good representation to a string representation to a solution or an individual if you were to do genetic algorithm? Why don't you raise your hand? Because I want people to sort of also think around. Okay, what's your name again?
My name is Paul.
Paul, yes.
Just a string of assign an ID to each city, and this the different IDs of the cities and all that.
The order of the cities in which the traveling salesman is going to explore, right? Okay, let's stick to that. How would I mutate it? Think about it. Think about how did you mutate it in n coins, and whether that will work for traveling salesman. So you have to raise your hands. Abdul.
Outside any cities.
Right. So can you see that just randomly taking one number and changing it to some other number doesn't work? So suppose my order is 9, 6, 3, 4, 2, 1, 5, 8, 7. If I had to do random mutation, I can't just say that, okay, I'm going to take this one and now I'm going to call it 8. That's not a valid solution. It's not a valid solution because now I'm visiting 8 multiple times. But then I'm going to assume that I can go from any city to any city directly with this. But this costs. You had a question?
I was just going to suggest you could swap.
Yeah. So that was the suggestion that we got. So instead of saying pick one randomly and mutate it, I'm going to pick two randomly and swap. Now, the idea of mutation sometimes it's very close to the general successor function. And so if I do random mutation, that works also. But can I do better than just completely random mutation? I pick two cities and I swap it if exactly. So so this is the a suggestion again. Is this a good suggestion? Yeah, I mean that's what I'm told. It's a good suggestion for TSPs. Random greedy swap. Pick two cities randomly. Swap them if the cost reduces. Okay.
Isn't that just hill climbing?
The mutation part is, yes. Let's talk about crossing over, because that is the fun part of genetic algorithms. If you can't think of crossing over, I mean the point of genetic algorithms is to move into non-local neighborhoods. If you are not exploiting that characteristic, then you might as well do greedy local, the greedy cleanup. So what could be a potential crossing over? So now I have two strings like this, two tours, and now I have to think about how do I compose them. Somebody is ahead of us. Think about it. Yes?
Take the first half of the first string and add some numbers and erase those numbers from the second string and then join them.
Okay. That's a at least a feasible suggestion. So I have this, and then I have 5, 4, 6, 7, 1, 3, 2, 8, 9. Wow, I'm good. And then you find a crossing over point. So you find this point as your crossing over point. You take the first this, and then you get rid of these. So you get rid of this, and this, and you're left with. Is this a valid crossing over scheme? Can somebody suggest something else, Manoj?
We'll find a common value between two and the next one replace them.
Find a common value between the two.
Like 4, 4.
Okay.
If you're going 4 to 2 and you're going 4 to 6 here, replace the 6 and 2.
Okay, I'm totally confused. So let's take 4 and find 4 here. Let's not do 4 because it's so big early in the game. Let's take 3 here. Oh yeah, 2 is also good. But same thing. Let's take 3 here and 3 here. Okay, then what do we do?
Swap the 4 and 2 because from 3 we're going to 4 there and from here 3 we're going to
Swap the 4.
swap the tops 4 with the bottoms 2.
Oh, right. But that's just one swap. We want to construct a full string that is based on both these. So right, so now you can start to think. I mean, my point of this exercise was not to teach you TSP. The point of this exercise was that you have to think carefully about what's a good crossing over function. Right? And it doesn't have to be, take this part of the string and this part of the string and put them together. You have to think about the problem structure, and do something reasonable with it. And same for mutation. So this is the crossing over that I have. I don't even remember that because I made these slides 1 week back. But let's see. Select the first city of one parent, so that will be 9. Compare the cities leaving that city. In both parents, choose the one which is shorter. So nothing is leaving 9, only 6 is leaving, let's assume this is cyclic, so this is Hamiltonian circuits, whatever. So 5 is leaving 9 and 6 is leaving 9. So we will pick one which is the shorter. So let's pick 6. Repeat. So now I am at 6, the one leaving 6 is 7, the one leaving 6 is 3, let's pick the shorter one. And we keep doing this. It might happen that both cities have already appeared, or one city has already appeared, then we choose the other city. If both cities have already appeared, we randomly select a non-selected city. Again, this works, I think, slightly better than your suggestion because it is sort of thinking about which is a better individual, a better state in the crossing over operation. Yes?
Then you only produce one string out of this 2 instead of 2, right?
You can always produce 10 strings. You can start from any random new point and then you get a new string. Right? So I started. Right. So I started with 9 and this is what I got. I could start with 5, get a new one. And technically, if you just think of it as cyclic, I can start from any point and get a new one. So
Even the goal of crossover is that we look beyond our local neighborhood and have a much bigger jump. Doing like this seems like we are still looking for individual cities and what is best around it, and that's how we are generating the full
the
structure.
point of crossing over is that we exploit the fitness of the individuals.
That's the selection part.
No, because these are good individuals. So we exploit the goodness of these individuals and get to a new successor that has the individual goodnesses of both of these parents. That's essentially the point of genetic crossovers, right? If we have a parent who's really beautiful and a parent who's really intelligent, we want the child to be both beautiful and intelligent, right? That's the point. Whatever is really good about this one and what is really good about the other, we ideally want to have a child that has the goodnesses of both. That's the high level point of it. Alan.
And the problem I've got with this, if you think about this in terms of a geometry problem, and we've got some metric between where we are and the actual solution, we'd like to think that the distance to the solution is getting shorter. But nothing I've seen so far tends to indicate that that'll happen as a result of crossover. With the Queen's problem, the combination of the two can be less. What I've seen is that we're good at eliminating bad solutions, but I haven't seen that genetic search is actually any better at getting us good solutions, because if we had this metric about how close we were to the solution, we could actually devise a better heuristic than crossover to get there.
Somebody's trying to respond to you.
So, this is the basic Darwinian argument, though, that if you get the randomness and then you keep cutting off the bottom, you gradually move better. It's like, as in P versus NP, it's often easier to compute whether you're close than to compute how to get close. So,
I think that's a better answer than I would have ever come up with. I really like this class. Okay, so I want to end this discussion with actually a very important point, which is something really recent that I heard about, so I wanted to share with you guys. So a lot of people, really rave about genetic algorithms. And by the way, I have a very interesting, you must see this. I have a very interesting video on the course homepage in the row of genetic algorithms. It is trying to recreate Mona Lisa by just circles or some such thing, and by evolving circles and overlaying circles on top of each other. If we have time, we can watch it. So, so lots of people really love about genetic algorithms. There's a full field of evolutionary computation. It has lots of conferences. It's one of the, it's one of an important areas in AI. However, as we were discussing, somehow, at least from what I have heard and what I have talked to people, most others don't think genetic algorithms to be that important unless you're really working in that area. People believe that there's no convincing evidence that this is a good algorithm by and large. So very recently I heard a seminal researcher from Berkeley, Christos Papadimitrou. I'm guessing many of you know that name, but if you don't, you must. He's a theoretician at heart who also works in theory of AI, and he claims that genetic algorithms do not offer convincing evidence because nature is not meant to optimize individual fitnesses. Okay. So then the question becomes, even if we take this premise at its level, the question becomes, I would agree with you if you told me what nature is trying to optimize. And that has been a question that has sort of stumped a lot of these thinkers who come along and say, genetic nature is like this, nature is like that, because people haven't been able to come up with convincing evidence for that as well. So, Papadimitrou has a slightly stronger answer to this, and that's why I wanted to share it. I'm not teaching this because I don't know anything about this, but I think this is a very interesting question to think about. And if you're interested, I can point you to his papers trying to talk about this. He claims that nature is not trying to optimize individual fitness. It is trying to optimize this other quantity called mixability. Okay? And think about what nature is doing. You don't know what kind of a mate you are going to get. So a stronger individual, a better individual, a fitter individual is not one who is individually fitter. He is probably one who can mate with many people and produce adequate or good offsprings. Okay. So what Papadimitrou shows or claims that he has shown, again I have not read it, and this hasn't made it to textbooks, so I can't claim this. What he shows in his papers is that genetic algorithms and the way nature works optimizes this other kind of fitness function, which is not individual fitness, but the ability to cross over with a large subset of population and produce good successors. A term that he defines as mixability, and a term that he conclusively claims that he has conclusively shown to be the case for genetics. And he also explains why people earlier could not think of it, because the mixability notions come up only when you run large simulations. You are not able to figure this out theoretically in the first couple of iterations. Something that, so you have to sort of read his papers, I have to read his papers to actually make sense of it. But I think this is cool, this is interesting, this is exciting, this is new, this is out of the box. And this may be the reason why, by and large, genetic algorithms have not been as successful as people would have wanted.
There is also an answer from machine learning which sort of claims that when the environment is changing, you want to preserve diversity in your population.
Mm-hmm.
And so there are some theorems to this effect that show that these kinds of algorithms help in preserving the diversity. And
genetic algorithms, right? Yeah, so that might be true. And that is very close to this notion of mixability, right? That I can get different kinds of input and I will still be able to be fit.
Right.
So if diversity is an issue, then I have a feeling the genetic algorithms will be really good if we trust Papadimitrou, which seems to make a lot of sense to me personally. And so the next question that is really a research question in my mind is how can we exploit what Papadimitrou tells us about genetics to understand where genetic algorithms will be really successful, like these dynamic environments, and exploit them there first, as opposed to trying local search with random restarts. That also comes to your question, which was where are they going to be helpful? A conjecture is in such terms.
Just a comment, like I tend to agree that even nature, it's not trying to maximize the fitness of one individual, but it's trying to make the species survive. So one individual is giving decently strong offspring, which means those people will survive. So the species, mixability.
So it makes a lot of sense intuitively, but again you have
But
to
our goal
you
is
have to
to
show
find
it
one
theoretically
fit,
in
right?
computation. Sorry?
But here the goal of the algorithm is to find the strongest.
The strongest, and
which is
therefore,
contradictory to
and
nature.
that's why I was raising the question that there are not that many empirical studies by and large that show that genetic algorithms are that. Although you are welcome to try genetic algorithms for your assignment, so to see, and if you are curious individual, see if suddenly bits change. Does genetic algorithms work better than everything else? I don't know. That's it's a research question now. Let's just finish the discussion on local search with talking about continuous functions. And so a long time back somebody had a criticism, maybe Abdullah, that most of what we are discussing is discrete. That's going to stay for the next couple of weeks, so I keep taking that criticism. But the idea of local search is an extremely general concept, and as we have hill climbing for the discrete version of the problem, if we had a continuous version of the problem, there is an equivalent or very close by an algorithm called gradient descent, which exploits the fact that it's a continuous problem, but the idea is again to go to greedy successors and go in the direction which is greedy in terms of optimizing my evaluation function. So now if we really had an optimization function like this, we had fxy equal to whatever it is, and you want to figure out the global optimum. And we want to use the idea that we have understood so far. What would we do? What we know is how to optimize a discrete function, and we are given a continuous function. What can we do?
Go towards increasing slope.
Contrast.
Yeah, exactly. Discretize. So we know how to solve discrete problem. We have a continuous problem. Let's approximate, discretize. Divide x and y into small circles or small squares, and do hill climbing. We know how to do hill climbing there. So that's the easier version. It's not always a good idea, and the reason it's not a good idea is because we're sort of not exploiting the structure of the continuous problems that we have at hand. We have context. So the gradient descent algorithm, and DJ will know much more about this algorithm than me because he's an expert in AI for continuous variables. But the idea is that you have a continuous function and you compute a gradient. So you compute a partial gradient. The gradient tells you in which direction of xi is my value increasing, and then I take a small step in that direction. And so I change my xi to be xi minus some step parameter lambda in the direction of the gradient.
But which xi to choose?
You can define a neighborhood function in many ways, but in this algorithm, I think we change all x's in the original algorithm. Yeah. So you change all xi's in the direction of the gradient, and then we move on. The question then it becomes is, what is the step size? Give me 1 minute. And the question is, what is the step size? And typically the first solution that people do is to search. So they choose a very small lambda and see that the new place that they will get to, whether it will increase the value or not. If it increases the value, great. Let me try and choose 2 times that size and see whether that is going to increase the value. If that is also going to increase the value, okay, let me do 4 times. And we keep doubling it, and if it starts decreasing, we come back, and that is the lambda that we choose. This is called line search. But there are many algorithms, so this is a full field in itself. You can read big tutorials on just gradient descent and how to do local search and these kind of methods in continuous variables. So I'm just giving you the feel of it, just to show you the analog. That if it's a continuous problem, we now have at least the background to think about it. The actual techniques may change a little bit because we can now use the notion of gradients. Yes, you have a question. What's your name again?
Chris.
Chris. Yes.
It sounds kind of similar to just like discrete hill climbing because you're following the gradient to the local maximum.
But we are doing lambda search, line search, so that completely changes that line. And the other question is, view will not be able to compute the gradient if you were in a discrete domain. So the notion of gradient itself is coming from the continuous variables, and that's why it is different from discretized local search.
Why is it minus, not plus?
Because you're minimizing the function.
Oh, yeah, okay, sorry.
Gradient gives you direction where the function is increasing. You want to minimize the function.
I thought you went to maximum.
I mean, in
You-
this case, he said
Wrong slide. Let's just make it plus to stay consistent.
Oh, okay. I didn't read the point number.
But in reality, if we had like a ball, it will go down on all slopes proportional with the slope on that parameter. So it should go down on xy's proportional with the slope for x in that particular point.
Yes,
rather
that's
than
correct.
choose only one.
Sorry, I
I mean, so the partial gradient with respect to each coordinate is going to be different. That is correct.
Yeah.
So it is not a joint gradient. It's not. You can't go in exactly the direction of minimization. That's why sort of making a computation tractable.
So there is, if you have a ball, let's
Right.
say in the middle of that graph, it will go down on all coordinates which go down proportional with the slope on that coordinate.
Right.
Rather than doing one coordinate at a time, as in this algorithm.
No, this is not doing one coordinate, that's what you mentioned. You reduce
No,
all
you
coordinates.
you are taking a step in all directions. So you are changing all xi's,
Yeah.
not just one xi.
Proportional with the
Partial
derivation.
derivatives.
Yeah.
On every step.
Sorry, I don't understand the issue.
No, I think he thought that you're doing it only for one xi.
No, so
Doing
we
it
are
for all
changing
xi.
it for all xi. Okay, I'll correct this slide for next time. Yeah, I should just add for that.
If you've got a nice, smooth, continuous function that's well behaved like that, there are easier ways to find the global minimum and maximum.
So you are assuming
Just
that
do your-
this is a non-convex function, like there are multiple hills in it. We're talking more harder problems. Of course, if it's a convex function, then there may be easier methods.
I mean, you just pull out your third year calculus.
I mean, usually when it's a function of several variables, you're not going to be able to get far with that.
Okay. Good, we spent this time completing this.